Hello, welcome. So, during today's recorded lecture, I'd like to continue on some of the talking that we've been doing about using logarithms to solve exponential equations. So maybe I'll take a tour of what we'll do today um, before we get started. So we'll start by talking through notions of radioactive decay. Those are modeled by exponential functions. The whole point of logarithms is to solve exponential functions, so we'll solve some of those. We'll carry on some interesting exponential functions where you need to use a novel trick, which I'll point out, a change of variables. So secretly, this will be like thinking about new functions as compositions of old functions and using that to solve. And then the last thing we'll do is a few more applications of exponential growth, um, in particular to populations and to compound interest. And I think we'll settle for getting through compound interest in this probably pair of recordings that I'll post. So with that out of the way, let's get started. So here is a situation you might find yourself having. You're studying some substance that decays radioactively, and these things have a thing called a half-life. And what's the half-life? It's just how long does it take for half of the material to decay? Um, Sometimes you'll see people talk about things like, what's the quarter life of something? That's how long does it take to reduce by a factor of 4? Um, Sometimes you also hear things called doubling time, which is how long does it take a quantity to double. That's not for radioactive decay, because radioactive decay indicates it's decaying. So let's go through one. So the amount of time needed for a radioactive material to decay, if you know its half-life, lambda. Well, how do you figure that out? Well, you start with some initial amount of it, and then every time it goes through one half-life, the amount reduces by a factor of 2, so it gets divided by 2. So what's this thing right there, this T over lambda? Well, that's just the number of half-lives that have passed. Each time one half-life passes, so each time T clicks up by lambda, that power on the 2 goes one more negative, and so you divide by 2 one more time. So that's where this formula comes from. Let's use this for something. So uranium-232, U-232, has a half-life of 70 years. Let's suppose you were tasked with storing a sample of 1 kilogram of U-232, and your storage needs to last until it's decayed down to just 1 gram. Well, here's a question. How long does your storage facility need to last? So how long will it take this 1 kilogram to decay down to 1 gram? So let's try to address this. We have everything we need to write down a formula. There's our initial quantity, Q0, 1 kilogram. I want to know how long it takes for this thing to decay down to 1 gram, so I'm going to set Q of T to 1 gram, and I want to know how long until. So that tells me that I need to solve for T. So let's do that. So I'm going to take 1 gram. I'm going to set that equal to 1 kilogram times 2 to the negative T divided by the half-life. Now what's the half-life? The half-life is 70 years. Cool. Let's carry on with that. So let's mess around with some units. So it's annoying that masses aren't in consistent units right now. Let's get a consistent unit. 1 kilogram is, of course, 1,000 grams. That's just what kilo means. And maybe I'll add those parentheses for emphasis. Now, a common mistake that happens is you might think that that 1,000 is also multiplied by that 2 and then raised to the power. That's not how order of operations goes, though. So you start with an input of t, then you make it negative, then you divide by 70. Then you put all that in the exponent of the 2, then you multiply by 1,000 grams. So the 1,000 isn't inside those parentheses, but that also tells you like what you need to undo first. I want to solve this for t. Let's divide by those 1,000 grams. All right, so let's carry on from there. So I guess here's one thing I see. The grams are going to cancel. And now I see 2 to a power. Well, this looks like an equation that is in exponential form. And all the unknowns are in the exponent. So if you want to solve that, putting it into log form seems a good idea. I'll get log base 2 of 1 over 1,000. You could rewrite that as 0.0001 if you wanted, but I think given that I struggled with counting how many zeros I should have, I'm not going to risk doing that wrong. So that'll be equal to negative t over 70 years. And then you want to fix that. I can now solve for t by, I guess, multiplying 70 years to the other side and dealing with that negative sign. And you might look at that for a moment and think, well, that's weird. That says that time is negative. But it doesn't really say time is negative because, well, in here, I see division inside of a logarithm. So it's the same as like 1,000 to the negative 1, right? I could pull that negative 1 out. So now I see double negative log base 2 of 1,000 times 70 years. Double negative becomes positive. Yeah, now it's clearly a positive quantity. You want to know what that quantity is? Well, I guess you just got to compute it. And I do have a Desmos Interactive pulled up to mess around with, don't I? Yeah, I'll just use the Desmos calculator, which I do know how to use, theoretically. Log. And I'm going to use the change of base formula because I don't see, obviously, how to get a subscript immediately. So there's the log base 2 of 1,000 times 70. About 697, well, I guess that rounds up 698 years. You know, cool. So let's carry on from there. One more application to do. And maybe I'll encourage you to like pause as soon as you see just how to do this, and then do it on your own. Come back, of course, and watch what I do afterwards. All right. So, interaction of solar radiation atmosphere produces an isotope called carbon-14. As a consequence, the amount of C14 in an atmosphere, and so in a living animal, remains constant. So, as long as an animal is alive, you can assume that it has roughly the same proportion of C14 in it throughout its whole lifespan. On the other hand, C14 also has a half-life of 55,000 years. So once the animal dies, it's not taking in C14 from the atmosphere anymore. So that half-life, that carbon-14 is going to continue to decay. Every 5,500 years, it's going to reduce by a factor of 2. So if you can figure out how much carbon-14 has decayed, you can figure out how much time has passed since that animal died. Let's see an exact example of that. So let's suppose you have an animal. When it died, you know that it should have had 4 grams of C14 in it. So the initial quantity of C14 is going to be 4 grams. And it looks like all the units are consistent, so I'll just suppress the units. I want to figure out when, so now when I dig it up, the animal has 0.01 grams. So if t is the time when you dig up the animal, there's an equation you get. So that means my equation to solve is 0.01 is equal to 4 times 2 to the negative t divided by, and I don't want to have to keep writing 5,500 years repeatedly, so I'll just put a lambda there and just remember that that's the half-life. So let's just take that, solve for t. And you know what I'm going to do? Let's divide by 4. All right, nice. And if you are of the mind to like know how to divide by 4. That's the result of division by 4. Right? 100 divided by 4 is 25. So that's how you do that. I now see an equation in exponential form with a base of 2. So that means that the log base 2 of 0.0025 is equal to negative t. And you know what? Now I'll substitute that in that 5,500. Because now I can solve for t. T is equal to negative 5,500 log base 2 of 0.0025. And I should remember it's in years. And you know what? If I want to actually know the size of this number, I'm going to need to compute that somehow. So let's go back to the machine. So I guess that 70 is now negative 5,500. Where's my backspace? There's my backspace. All right, and then what do I have? It was the log base 2 of 0.0025. One more zero? My short-term memory is very bad. I'm going to have to double check. Yeah, cool. That was about 47,500 years is where I'm going to end it. Because that 5,500 year statement of the half-life wasn't that precise anyway. About 47,500 years. Cool. So, how long has this animal been dead? 47,500 years. So, I guess that tells you a lot of things. Like, was this animal coincidental with the dinosaurs? No. Is that the right time for him to be the most recent ice age? Maybe. I probably should have known that before starting this lecture. Nice. So, um, biologists, paleontologists, they use these things when they want to study how old something is. And carbon-14, because its half-life is 5,500 years, it makes for a good tool for picking up that sort of information. All right, so let's change gears a bit. Here's another interesting type of equation to solve. 4x squared minus 2x minus 1, I think I said a digit wrong, equals 0. Let's try to solve that. And so you see something that's a little bit off-putting. There's multiple exponents, yeah, but there's also this like minus 1, which is going to complicate things. So here's how I'm going to advocate solving this. You look at this equation. I see a bunch of different exponents, but really they could all be the same exponent, right? That 4 to the x, well, that's 2 squared to the x, which is 2 to the 2x or something, or maybe 2 to the x squared. Yeah, that looks useful. So let's use that. So let's replace 4 to the x by 2 to the x squared and see what that does to this equation. They're equal, so we can do that. There's 2 to the x squared plus 2 to the x. Ooh, interesting. There are two different 2 to the x's. Minus 1. Ah, so what does that tell me? So what can you see here? You see every time that there's an instance of a variable, it's wrapped inside of a 2 to the x. So this is really like a composition of functions. And I can see that composition of functions if I like create a dummy variable that is 2 to the x. So let's use u equals 2 to the x and see what that gets us. So that will turn this 2 to the x into a u. Then it gets squared plus 2 to the x is u minus 1 equals 0. Oh, I should remember the equals 0. Oh, nice. Well, that's something that I know how to solve. That's just like a quadratic equation. So I took an equation that was too hard to solve directly. I've introduced this dummy variable u. I don't really care about u, but that dummy variable has let me turn this equation that's too hard to solve into something that looks doable. And I guess the downside of this is like not live is I can't have you just compute this quadratic, the solution to this quadratic on your own. I have to actually do it. So I guess if I must, I must. So that doesn't look like it's going to factor in any nice way. So let's just use the quadratic formula. U equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. A is 1, so let's just divide by 2. All right. And a lot of times with the quadratic formula, the hard step is actually writing things down. These numbers don't look like they're too gnarly. There's negative 1 plus or minus the square root of 5 all over 2. 5 has no square factor, so I can't simplify. So you might say, great, I'm done. I've solved. But I haven't really solved because that's u. I don't care about u. I want to know what x is. But u is 2 to the x. So let's plug in 2 to the x for that u. So I get 2 to the x equals negative 1 plus or minus the square root of 5. And those of you who are paying astute attention will notice something interesting right now. I'm going to not notice it just yet. Something silly is going to happen in a bit. So 2 to the x is equal to that. Well, I guess that means I know how to solve for x. This is an equation in exponential form. You want to know what x is? Put it into log form. And what do we get? We get log base 2 of negative 1 plus or minus the square root of 5 all over 2. Looks like there are two solutions to this equation. And again, I'm going to say, well, let's do a quick check. We can check for solutions to equations by looking at a graph. Let's do that. Where are we? That's this one. Let's pull up that graph. And I guess we also saw these two solutions at x equals negative 1 plus or minus. So I'll graph the plus first. The square root of 5 all over 2. All right. There that is. Well, of course that's not right. I left out the log base 2. I'm going to take the log of all that. Now I need to divide by the log of 2 to get a base 2. Oh, nice. Now that looks pretty good. That looks like the solution. But there were two solutions, right? Let's test the other one. The other one said it was at the same log, but at negative 1 minus root 5 over 2. That's weird. I don't see anything. What does that mean? And, well, secretly, I know what that means. This is not defined. So let's think about why. I think I see a negative inside of that log. Let's go back to the notes document and see. So let's see. Right here, I see 2 to the x is equal to these two different numbers. But if they're both negative, this thing winds up being negative. Only the positive choice walks. In fact, let's make some space to explain why. Since 2 to the x can't be negative. So I'll go ahead and just indicate that it has to be the plus choice. So x was -1 plus the square root of 5 over 2. Very nice. Well, log base 2 of that. All right, let's crunch through one more real quick. We'll play the same game. I think that I won't do the Desmos Interactive because that's very slow. Let's solve 9 to the x plus 2 times 3 to the x. Remember, this 2 is not in the base of that exponent. It's just multiplied after you exponentiate. Minus 4 equals 0. So between the 3 and the 9, I think I see u equals 3 to the x being useful. And, well, let's experiment with y. So 9 to the x is equal to 3 to the x squared. Yeah, that's right, right? Right? Exponents multiply. Is u squared. So let's make that substitution. I get u squared plus 2u minus 4 equals 0. Yeah, that looks like something we can solve. It's like I'm getting u equals negative b plus or minus the square root of b squared. B squared is 4, minus 4 times a is 1 times b is -4. Double negative is going to become a positive, all over 2a. So looks like I'm getting u equals -2 plus or minus root 20 all over 2. But you keep staring at that a little bit longer. 20 has some perfect square factors. -2 plus or minus 20 is 4 times 5, so I can pull out the 2. Root 5 all over 2. Everything in the top's even. That's a multiple of 2. That's a multiple of 2. The denominator is only a multiple of 2, so those 2's can cancel. So that's going to get me u equals -1 plus or minus root 5, no longer divided by 2. And then you see the same issue. If you take the negative choice, you're going to get a negative number. No, I guess I don't see that till the next step. So that means 3 to the x is equal to -1 plus or minus root 5. Only the positive choice, though, is in the range of 3 to the x, because 3 to the x has to be positive. So I'm getting x equals log base 3 of -1 plus root 5. And if you've got the time, I'd encourage you to go through and read that off from a graph too. All right. One last one before I stop this recording session. This one's going to require a fundamentally different technique. 7 times 2 to the x equals pi times 3 to the x plus 1. Let's try to solve that. And I can't use the same trick this time, right? That's a 2 to the x. That's a power of 3. Those two don't have a common factor of their base. They're not, one of them's not a square of the other. So what can I do instead? Let's know that they are logs, right? Let's try just hitting both sides with the logarithm and see what happens. And any log will do. So I'm going to even stay nice and ambiguous. I'm not going to pick a base. It's just going to be log. So maybe most computer systems would interpret that as log base 10, but you don't have to. And you might say that doesn't make the problem better, or that makes it worse. Now both sides have a log around it. You could cancel the logs, but that would get you back where you started, so that's not a good idea. So why did you do that, Chris? Well, here's why. This log wants to undo that exponent. This log wants to undo that exponent. They can't yet because there's more than just an exponent inside the log, but it's just multiplication. So what do I actually see? I see log of 7 plus log of 2 to the x. Ooh, that looks pretty nice. Equals log of pi plus, well, let's close that parentheses, log of 3 to the x plus 1. Nice. Ooh, well, that's just a number and an exponent. That's a number and an exponent. Logs know what to do with those. They can pull those exponents out. So I'm seeing log of 7 plus log of 2 times x equals log of pi plus log of 3 multiplied by x plus 1. Ooh, and here's some stuff you see. Let's look at each ingredient. What is this log of 7? That's a constant. There's no x's in it. Log of 2, that's a constant. There I see x to the power 1. Here I see a constant. Another constant. There's an x, that's a constant. So this is a linear equation. I know how to solve linear equations. Like, you get all the x's onto the same side, all the non-x's onto the other, you do some division, and you're done. So let's try to get all the x's onto the same side. Goodness, so I guess I better start by distributing this out. Maybe I'll even try to get all the x's onto this side. Sorry, I was pointing. You can't see where I point, though. Onto this side. So, log of 7. I'm fine with that being where it is. Let's subtract log of pi to the other side. Let's also subtract log of 2 times x to the other side. All right, I want all the x's onto that side. Plus, let's distribute log of 3 times x plus log of 3. Good. That's progress. Find myself some more space. This can go to the other side. Log 7 minus log pi minus log 3 equals, let's factor the x out of the side that has the x's. X times log 3 minus log 2. And you'll notice I wrote them in the opposite order. That's because I like to see the positive thing before the negative thing. Right, I'd rather see log 3 minus log 2 than negative log 2 plus log 3. All right, well, I'm basically done now, right? Now you just need to divide by whatever's next to that x. Looks like the answer I'm getting is x equals log 7 minus log pi minus log 3 all over log 3 minus log 2. Nice. And, well, maybe I'll give you this task to do right now that we've gotten an answer. Get a decimal approximation for that. And maybe more than that. I didn't actually specify a base the whole time. You may have assumed I meant base 10, but they better give you the same answer. See if they do. And then finally, the last thing I'll have you do is I'm going to have you check by graphing. That is, graph both sides of this equation. See where they cross. It looks like you're going to get a unique x value where they cross. Where they cross, that's your solution. Read off that x value. All right. Well, I'm going to take a quick break. I'm going to post this to the web page. More recording will come out in a bit. All right. Well, I will see you.